Well, good morning. My name is Adam. I am the project manager for Rabbit Trails. Rabbit Trails is one of 4 teams participating in the Autonomous Walking Robot competition this semester. As most of you know, the competition will be in E217 in approximately 53 hours. So, what is this competition all about? Well, the goal of the competition is to design and build a small walking robot that can navigate an obstacle course. The obstacles in this course will be 2-inch tall walls, and the stairs that we'll have to climb over will be 1 inch high each. The maximum size of our robot was set at 7 inches by 7 inches by 7 inches, and the maximum money that we were allowed to spend was $300. Remote controls, wheels, and climbing over obstacles are all grounds for disqualification. So, what we're going to talk about this morning are the specifics of our 2 missions. Our mechanical design will show you a system-level block diagram, the components we selected, how we're using our sensors, our software, and then we'll talk about how we spend our money and our time. So, the 2 missions that I mentioned, the first one consists of walking along a flat surface, and our robot will have to avoid randomly placed obstacles while searching for the end cell. One thing that we do have working to our advantage is the fact that the locations of the start cell and end cell have been defined for us, and they're marked on the diagram here. And then mission 2 is the exact same as mission 1, only stairs will be placed in the center of the course. Speaking of stairs, here's a picture of the actual stairs we'll be using. They are 7 inches wide by 1 inch high by 2 inches deep. So with that out of the way, we would love to show you our robot. And to do that, we have our lead mechanical engineer, Dustin Sackett. Dustin designed and manufactured bugs from scratch. Sorry, he's not a mechanical engineer. He's actually an electrical engineer, self-taught mechanical engineer. Here he is.
Thanks, Adam. Good morning, everyone. And as Adam said, I will now talk about our mechanical side of the project. Given the constraints of the competition, as well as our limited budget, we decided early on that it would make the most sense to design and fabricate our robot from scratch. This allowed us to fine-tune our robot as we saw fit throughout the course of the project. On our left, we have our original prototype. On our right, we have the final and complete form of Bugs. As you can see, it came a long way over the course of the last 15 weeks. At the core of our project, we revolved the entire system around a printed circuit board, which we use as the main body. We use this as an interface to integrate all of the electrical and mechanical components of the system. This proved to be valuable in ensuring that our robot could fit in a 7-inch cube. Next, I will discuss our legs, which are the most important part when it comes to walking. And early on, we realized that walking wasn't the hard part, it was ascending and descending these stairs. So we revolved our design around that task. What was important there was having enough vertical range of motion to get up and down the 1-inch stairs. Our final design allowed us to move 1.5 inches, which proved to be more than enough. On our left, we have the lower leg segment, which was a custom 3D printed part that allowed us to swap out feet as we saw fit. And the final foot design was a 2-inch circular foot that proved to be very beneficial when it came to balancing on 2 legs. On our right, we have the servo brackets, which we found out really early on that if we did not have a rigid connection between all our mechanical components, the robot would behave unpredictably and made it a very difficult platform to code on. So that was one of the big obstacles we had to overcome. I will now hand it off to Derek to discuss the block diagram.
Thank you, Dustin. So, as you can see here, this is our block diagram, which consists of our power supply, our servos, and our microcontroller. So with our base diagram, we got our 7.4 battery going directly into our microcontroller, which will be sending input to our servos and our sensors, and our sensor will be returning a feedback to our microcontroller. To the other side, we got our regulator coming from the battery, sending its input to its servos, which will be sending its inputs to its shoulders and its knees in order to get our robot to move. With our components, we chose to use a 7.4 lithium-ion battery, which lasts up to approximately an hour and a half. And we use that to feed that to our Arduino Mega, which is our microcontroller, which operates between 6 and 14 voltages. To control our servos, use the ADA servo driver, which is our servo shield, where we connect all our servos to in order to get our servo to operate for our ASIC joints in order to move and navigate. And with the servos, they operate between 4 and 6 volts, which is why we have a voltage regulator to step down the voltage to 5 volts. So we got it in the safe range. Our servo motors, they rotate at a maximum angle of 180 degrees. But for our safety precaution, we chose to do 140 degrees. And then with that being said, it also operates with a torque up to 34.7 ounce inches. But the robot is required to operate at a torque of 10.25 ounce inches. With that being said, one thing I have not mentioned was that another important component, which is our sensors in order to navigate. The sensor here will be discussing that.
Sensor is the most important part of the robot. It is the eye to detect the wall and stair. We use 6 of that, 4 in front and 2 in left and right side. The effect range can go from 6 to 18 centimeters. Because we built our own robot, so we need to figure out how to the sensor placement problem. So here's our solution. We customize our front sensor bracket. From picture, we can see 2 in front sensor. We use it to detect the wall and stair. The 2 diagonal sensor, we use it to central the robot before it going up to stair. Why we need to centralize? Because we build our own robot. The width of the robot is very close to the stair width, so we don't want it to fall down when it's coming. Here is the diagram showing you guys how our diagonal sensor works. When the robots go close to the stair, if the diagonal sensor detects that it's not in the middle of the stair, it will shift to left or right to make sure that it is in the middle of the stair before it's going up to stair. Next, Yadia will talk about how our software works.
All right, good morning. So we knew that in order for the robot to be able to clear the course, he needed to be able to do a lot of small functions like walking, which is very basic. So our walking code, you can actually see some pseudocode up there. Because our mechanical design is so simple, it's actually very easy for him to walk. So what we do is we lift 2 diagonal legs, move them forward, downwards, and then backwards. So that'll make a pushing motion in either way, directing. If you do both of these in a fast pace, he moves sideways to both sides, so then he ends up walking straight. We have an incrementing step variable at the end. So basically, in order to know when the robot is finished, we need to tell him that he has walked over how many steps, depending on the width of the cells. So we have actually checked, and our robot takes about 15 steps per cell in the grid. So that increments every time he finishes 1 step. So another basic function that he has to be able to do is turn. So turning is basically like walking, but instead of using all the 4 legs, we just have 2 legs moving and doing all the work. So if we repeat this motion over and over again at a rapid pace, he'll actually turn instead of walk straight. You'll notice that instead of incrementing steps here, we actually have a switch direction variable, because every time he turns, he won't be facing north. So the way that we set this up will be actually explained in the navigation algorithm, which I'll cover right now. All right, so for navigation, we know the start cell and the end cell. So what we ended up doing was give it a priority to northeast. So it starts walking north. Whenever it turns, it's going to update that variable in the turning function. So it's going to start north, like I said. And then when north, it's just gonna walk straight. Once it reaches a wall, his second priority is east. So he'll try to turn that way. If there's a wall in that spot, he's gonna, as a last resort, turn west. If he's actually facing east, his priority changes to north if it's possible. So he'll walk straight, but his left sensor is always gonna be checking to see if it's possible to turn back north. And once it reaches the amount of steps that we have calculated, it'll stop. So right here, we only have two functions, the north and east. It obviously has two more for the other two directions. And for the stairs, the only thing that changes is it's gonna be pinging for the stairs for the second run. And then if it detects it, the stair code is hard-coded, so it's just gonna go over and then navigate again with the same algorithm. And here we have kind of a video showing how that actually works. So as he's walking straight, he'll detect the wall in the front and turn automatically. And then when he's walking straight again, he knows that it's no longer north that he's facing. So we don't want him to reach the end of that cell because he'll get trapped. So he's pinging the side sensor at all times. And once he actually detects that there's no wall, he's gonna walk a little further just to make sure he doesn't get stuck when turning. And then he'll turn and continue to walk forward, and now it knows that it's walking north once again. So in order for everything to work, we need money, obviously. So Jimmy's gonna talk about our budget now.
Hello everyone. So we have $300 budget for building a walking robot. So far we spent $272 for our part. And we spent nothing for the aluminum chassis, which cost on the road from $70 to $90. And we want to say thank you to Dustin, who spent a lot of time to do all the mechanical work. For Luno Omega, we spent 12% of our budget. The soft IR sensor, 22%. The servo motor and controller, 18%. Battery and voltage regulator, 14%. We also use 25% of our budget for spare parts, like a sensor or motor, just in case one broken. And we still have $28 for our remaining budget. Next milestone. So first we build a sample leg, and we use a servo motor to move the leg. We check how high the leg can move. We record all the dimensions for the mechanical design. For mechanical design, we make a decision to build our robot from scratch, and with 4 legs, 2 servo attached to each leg. For the power supply, we're looking for a lightweight and large capacity battery. We spent 3 weeks with all the mechanical design, manufacture, and assemble. We put all the parts together and install the power supply on March 20. And for the stair identification, we use distance comparison between 2 front sensors, one top and one bottom, to detect the difference between stair and wall. On April 4, our robot started walking. Because we work with our sensor first, so we had a time with optical avoidance. So when our robot walks, it will check in the front. If it see the wall, it will call turning function. If it see the stair, it will call climbing function. We are almost done with the stair climb and the stair distance algorithm. And we also add a big feed for our robot more stable when it walks up and down stairs. And our robot is ready for competition on May 7th. Thank you for listening our presentation.